All right, so yesterday we finished up class talking a little bit about resonance. Resonance is one of the big themes in organic chemistry. It will not go away, so we've got to make sure that we master this early and that we understand it relatively quickly. We're going to spend today and tomorrow going over this. So yesterday I presented an example of resonance where I drew this ion called the formate ion. And if we look at the structure on the left, which is what Lewis dot structure predicts, we would predict the carbon-oxygen single bond should be a little bit longer than the carbon-oxygen double bond. But in reality, when we look at this formate ion, both carbon-oxygen bonds are the same length. And so Lewis dot structures don't always do an adequate job of describing where electrons are located within a molecule. So let's take a look at another example of resonance, specifically regarding molecular orbitals. Yep.
So how are we going to know whether or not a double bond is shorter?
We're going to go over it. There are some key things you can look for, but it takes a little bit of practice, and we'll go over it. Okay, so let's take a look at this example. We've got our allyl cation. And if we draw out the allyl cation, we've got a carbon here, double bonded to another carbon, single bond to another carbon, hydrogen coming off. And the carbon on the right is actually a cation. So this is a really common cation that's found in organic chemistry, but let's really quickly identify the hybridization of each of these carbons. What's the hybridization of the carbon on the left? Is it sp, sp2, or sp3? sp2. Okay, what about the one in the center? sp2. What about the one right here? Huh? There's some disagreement. It's only got 3 attached groups, therefore it's going to be sp2. So all of these carbons are sp2. So let's try to draw out our molecular orbital picture, and I'm going to shorthand it a little bit. I'm not going to draw the sp2 lobes. I'm only going to draw the remaining p orbitals, and I'll show you what I mean by that. So we've got a carbon, carbon, carbon. I'm going to angle this one back a little bit. Hydrogen here, and a hydrogen here. So if we look at each of these carbons, they all have a p orbital that's left behind, right? Oop, sorry, this should be drawn as a single bond. I'm messing up your notes. There we go. So we've got all of these p orbitals. If we look at the p orbital over here, they're overlapping, forming this pi bond, right? And then the carbon on the right, what's in the p orbital? Yeah, trick question. Nothing. The p orbital is completely empty right now, so it's got a positive charge in there. And so if we look at this molecule, we can actually draw that pi bond flipping from that left-hand side over to the right-hand side. So those electrons are actually aligned with that vacant p orbital, and they can delocalize into it. So let's redraw this down below. These p orbitals are still there. But now our pi bond is located on the right-hand side, and the carbon on the left is positive. This is what's going on when we're looking at resonance structures, is the electrons aren't stuck in one position. They can actually delocalize across multiple atoms in a molecule. So if we think about this, the positive charge, where is it located? Is it on the left or on the right or on both? Both. So in this case, The reason why resonance occurs is that we can distribute a positive charge across two different atoms. That stabilizes the molecule significantly. So instead of one atom being stuck holding that burden, it can share that burden with another atom.
It's on both at the same time, or it could
Yeah, that's a great question. In this case, it's on both at the exact same time. So each carbon is sharing a positive 1/2 charge instead of a positive 1 charge.
All three of them?
Nope, just the two end ones.
What if it was an oxygen instead of carbon?
We'll see some cases where we can't push electrons, but in this case, because the p orbitals are aligned, those electrons can actually delocalize across all of the p orbitals in this system. So the reason why this is so favorable is we're taking that positive charge and sharing it across a much wider distance, and we're not forcing it on any one given atom. Yeah?
This is like physically because the electrons just kind of bouncing back and forth.
Yeah, so in this case, the electrons can actually delocalize all the way through all of those p orbitals all at once.
Okay, so they have it's happening so fast that it's basically like there's two places at once.
Yes, exactly. Electrons, because they're so small, they behave like waves. So these electrons in that pi bond are actually located in all three p orbitals at once, essentially. Okay, so this is a unique example. Yep.
There has to be a p orbital involved? Like
Yeah,
it's
with resonance, you'll always see p orbitals involved. So the electrons have to be delocalized through p orbitals. They don't get delocalized through sigma bonds.
Okay. So
Yep.
it can't be sp3.
What's that?
It can't be sp3.
Yeah, it can't be sp3, but we're going to see some weird examples a little later.
Where does the double bond go?
So in this case, the double bond is shown as the pi in the green, and so that double bond is actually delocalized across all of the carbon atoms now. So if we think about the carbon-carbon bonds in this molecule, are they double bonds, single bonds, or are they bonds and a half? Bonds and a half. They're a hybrid of a double and a single bond because of that delocalization of electrons. So let's look at another kind of weird example. Oop, if I can spell another. That looks really similar to the allyl cation. But this is got a negative charge on it instead of a positive charge. So we've got a carbon here. This time the carbon on the right has a lone pair on it, meaning it has a formal charge that's negative. If we look at the carbon here, what's its hybridization? sp2. What about the one in the center? sp2. What about this one? This is tricky. So I'm going to write this down as sp3 question mark. And I'll show you guys why. So Vesper theory predicts the last carbon to be sp3 slash trigonal pyramidal but if we actually look at this experimentally, it's trigonal planar, not trigonal pyramidal. sp2 slash trigonal planar. So let's try to rationalize the experimental data with the discrepancy in Vesper theory. So I'm going to do the same thing that we did before, and we're just going to assume that it's sp2 and try to rationalize why it's sp2. So I'm going to scroll down, and we've got a carbon here, carbon here, carbon here. Got hydrogens coming off. And we need to include those p orbitals. So the double bond in the Lewis dot structure shows this pi bond should be over here. And then in this orbital, we've got a lone pair of electrons, and this carbon is negative. So what happens is this negative charge can actually delocalize across all three p orbitals, just like we saw that cation delocalizing. So let's draw the second structure, where we've got a carbon here, carbon here, carbon here. And let's draw in our p orbitals. Got one sticking up, and all three carbons. This time now we've got a pi bond located over here, and we've got our lone pair on the left-hand side. So is the negative charge truly located on this carbon, the one on the right? No, it's shared evenly between the carbon on the right-hand side and the left-hand side. So in this case, each of those carbons has a charge of -1/2. What about the bond order? Is it a single bond, double bond, or bond and a half? Bond and a half. So resonance is used to describe this delocalization of electrons in here. Why doesn't this work if it's sp3? Yeah, exactly. If we've got an sp3 carbon on the end there, we don't have an aligned p orbital to allow that negative charge to delocalize. So by having this switch to sp2, we can actually show delocalization of electrons, and that's exactly why Vesperi theory is not correct.
So would it be safe to say that all resonance structures would be sp2 geometry, or is there like a time that it's not?
If there is the option for electrons to delocalize, they will. So you can always assume if there is that option, it will delocalize, therefore that will be sp2. If there is not an option, meaning there's not a p orbital next door for it to go into, it will not turn into an sp2. Yeah, good question.
What does it mean by the bond and a half?
So if we look at, let's actually go up here. If we look at this carbon-carbon bond on the left, it's not really a double bond. It's actually more like a bond and a half. And this one's not like a single bond, it's more like a bond and a half. Because these electrons are migrating across all three carbons at once, they don't really behave like a true double bond or a true single bond. They're kind of in between.
Okay. I still don't get why that's not sp3.
So if it were sp3, we wouldn't have a p orbital. We need the p orbitals to align for this negative charge to migrate all the way across all three carbons. Without that p orbital there, those lone pairs would be stuck in an sp3 orbital and they'd be out of alignment and couldn't be shared. We have to have p orbitals lined up in order for those electrons to be transferred in a pi bond.
So this kind of thing, what happens in sp2 only?
It occurs in sp2 or sp. You have to have p orbitals for resonance to occur.
Does that say sp2 there?
The two over here.
Oh, no.
So in this case, sp3 is not correct.
So when you ask to draw a resonance structure, there's no way it will be sp3.
We'll go over some unique examples, but I just wanted to show this as an elementary example of what's going on in resonance. Go.
Are there like rules or like parameters when this occurs, or you just
Yeah, I'm going to go over the basic rules for resonance here. So let's actually switch to that. That was a good segue. So let's talk about drawing resonance structures using bond line notation, and there are a handful of rules to remember. So let's make a list of basic rules. Rule number 1. Don't break sigma bonds. The only electrons that move in resonance structures are going to be electrons located in p orbitals. Sigma bonds, by definition, are not going to be p orbitals in organic chemistry, at least. So don't ever worry about the sigma bonds. Leave those as is. Second rule. Don't exceed an octet. If I see a carbon with 5 bonds on it, what do we call it? Texas carbon, and then you get a frowny face, and we both feel bad. Rule number 3. Only move lone pairs or pi bonds. In the last 2 examples I showed you, we showed migration of pi bonds across multiple atoms. And in that second example, we saw the migration of a lone pair across multiple atoms. Those are the only electrons we can move in resonance structures. Yep.
So a lone pair in like an sp orbital could move, or an sp2 orbital?
No, the lone pair has to be in a p orbital in order for it to delocalize. Yeah, that's a good question. All right, number 4 is we're going to use arrows to push electrons, and I'll show you how to do that. And so let's say I've got an arrow like this. What this arrow means is that the left-hand side is going to be your electron source, meaning your lone pair or your pi bond. And the side of the arrow with the head is going to be your electron destination. Okay, so let's use these rules to show resonance structures of our last 2 examples, but we're going to use bond line notation instead of molecular orbital theory. All right, so in our first example, we had carbon, carbon, carbon. I'm going to draw all of our atoms for right now, just so we can see what's going on. We had a double bond here and a cation here. With the resonance structure, what we would do is move this pi bond over here, and we would represent that by an arrow. And what we need is a double-headed arrow, which you guys saw me do before, between our new structure and the old one. So now we've got a carbon here, hydrogen, hydrogen, hydrogen. But now our double bond is on the right-hand side, and our positive charge is located over here. Last thing we need to do to show that these are a set of resonance structures is we bracket them in. So let's try to show what this looks like using dashed lines a little bit. So I'm going to put an equal sign here. Got a carbon, carbon, carbon. Hydrogen's going down. I'm going to slide this over a smidge. Let me scoot this over a little bit more. Oh no, what did I do? Sorry, guys. What's the bond order in this molecule? Is it a single bond, double bond, or bond and a half? Bond and a half. So I oftentimes will draw this using a dashed line. And then if we think about our charge, we said our charge was delocalized over here and over here. So you can really think of the resonance structure on the left describing the molecule on the right. Yep.
So the dotted line is just representing the double bond rings,
Exactly. The dashed line, or the dotted line, I should say, represents that bond being shared. The one thing that confuses a lot of people is they think, well, these two are the same molecule. It's just flipped over, right? But with resonance structures, what we're doing is showing that delocalization across multiple atoms, so we do have to show both of them to indicate that that positive charge is being shared. Is there a question in the back?
So on the right side of the molecule, do we not have to draw an arrow of the charge going backwards if it's the resonance structure?
So if there are more resonance structures possible besides just two, you would continue on and continue pushing electrons, and we'll see some examples of that fairly soon.
Okay.
Yeah. Yep.
So is this kind of just like your London dispersion force example?
It's a little bit different, but in this case, we're just showing electrons moving across the molecule to represent the fact that they're not located on one atom or another, that they're actually shared across multiple atoms. That's really all resonance structures do.
Just for a second.
Yep.
Thank you.
Okay, the example I like to use when I'm describing this, I wrote it down. It's really cheesy, but I think it's effective. Let's say I've got a blue horse, and its alternate resonance structure is a red donkey. And we bracket these together to show that it's not that what we have is a red horse or a blue donkey. What do we really have? A purple mule, right? So we represent the two individual forms, but the reality is that it's a hybrid of both of them. So that helps some people think about it. It's not that it's flip-flopping back and forth really rapidly. It's actually just representing a purple mule, and we're showing what the two individual components are that make up a purple mule. All right, let's take a look at our second example really quick. So we've got carbon, 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 hydrogen. If we were to draw the resonance structure for this, now what we do is we move the negative charge, meaning the lone pair, over to this position, and then we dump this pi bond over to the carbon. So we always push electrons. We don't ever push positive charges. So now we've got a double bond here, and now the lone pair is on the carbon on the other side.
Is that on the previous example you moved the...
So on the previous example, we moved a pi bond, which is okay according to our rules. But on the bottom example, we were moving a lone pair and a pi bond. You can move lone pairs and pi bonds, but you can't move any single bonds, for example. All right. Does that make sense? No? It takes a little while, I know.
Why can't you just move pi bond to the other side, just like the last example?
Yeah.
So let's do that. All right. I'm going to erase this for now. So you're saying, what if we erase these for now? We can add them back in later. You're saying, why don't we move this pi bond over there?
Yeah, and move the electron to the other side.
So remember, the electrons have to be pushed in order. So you can't have an electron just magically pop over to the other side. It has to be pushed over to the other side. So if we move...
Step by step?
Yeah, you have to do it step by step. So in this one, if we did this,
So we can move just electron one space.
yep, only move electrons to adjacent atoms. What's the problem with this structure?
There's too many bonds.
It violates the octet rule. So in this case, we can't move that pi bond over. We can only move that lone pair over. So be careful to always check for your octet rule.
Does the browning fail?
I'll do it on your guys' papers. All right, so let's move this back over here and here. All right, let's do another example.
Oh, wait.
Oops, sorry, I'm going too fast.
No. So how would you draw this with the dashed line? Because I had that lone pair of electrons. Where do you put those lone pair of electrons in the...
Yeah, so let's do this over here. We'll do our hybrid structure, or a purple donkey. It would still be dashed, but this time we'd have a delta negative on each side rather than a delta positive. That negative charge is actually going to be shared by both of those carbon atoms, so we don't really show it as a lone pair because it's being shared across both. Instead, we just use delta negative.
It's inferred that there would be a lone pair because it's negative.
Exactly, yeah. If you do have a delta negative, that means that it's a lone pair shared across multiple atoms. Yep.
How would you know a lone pair if you weren't writing the C carbons there, or the C's for the carbons? Could you just have the two dots and then the
Yeah, normally what you'll see is instead of people drawing the dotted line representing a double bond, is the preferred form of resonance structures is just draw both and use arrow pushing. So the option on the left is the preferred way of drawing resonance structures. Make sure you bracket them in though and you have a double-headed arrow. Yep.
Do you need to put arrows on both sides? Or is it okay just to have it on one structure? Or should I put opposite arrows on the
You can just have it on one structure, but let's take a look at this next example. So in this example, we've got the carbonate ion. Whoops. So the carbonate ion has lone pairs here. And this oxygen has a negative charge. And this oxygen has a negative charge. So let's try to move some electrons around. I'm just arbitrarily going to pick one of the lone pairs, and I want you guys to yell at me if you think I'm picking the wrong lone pairs. Let's pick these two. Why won't that work? Yeah, we'd have a Texas carbon. We'd have a frowny face, and we'd both feel bad. So let's avoid that. We can't push those electrons down without violating the octet rule. So let's move these electrons, this lone pair, and I'm going to dump it down there. What's wrong? We've got a Texas carbon, but we've got a way out of that Texas carbon.
Move the double bond.
Yeah, let's move the double bond up here. The other way, the last time I was showing you guys taking the lone pair down here, we would have to break a sigma bond in order to alleviate that Texas carbon. That's not allowed. But pushing in from this oxygen, we can alleviate that Texas carbon by removing that pi bond. So let's draw the next resonance structure. So we've got an oxygen carbon, but now our double bond's over here. Okay. Is there anything else we can do? Yeah, let's do it again. So this time I'm going to move one of these lone pairs over here. And then this lone pair over here. Or sorry, that pi bond, I should say. So now we've got an oxygen double bonded to a carbon. Oxygen here. And we've got a negative charge there and there. Can we push any more electrons? Not without duplicating a structure that we already have drawn. We could try to, but we'd be just repeating ourselves. So these are the three potential resonance structures for the carbonate anion. So if we're considering the oxygen, what charge does the oxygen have on it? Is it a negative charge? Is it a negative 1/2? What would it be? Would be negative 1/3? let's think about it this way. We've got an overall charge of -2 that's being shared across 3 atoms. So it'd be -2/3 on every one of those oxygen atoms because we're distributing the electron density. So let's draw our hybrid. And I'm just going to draw -2/3, -2/3, -2/3. So the hybrid is showing us that each of these CO bonds is actually the same length, and that the negative charge is being shared evenly across all of those oxygen atoms. This is much more stable than forcing one of the oxygen atoms to carry a full negative charge. It's making it a little bit less unstable by reducing that charge to -2/3. Does that make sense? It takes a little bit of practice, I know.
How can you get that negative purely?
So our overall charge, if we look over here, was -2, right? We've got a negative here, a negative
We
here.
have 3 structures, so.
But this overall -2 is being shared across all 3 oxygens. So 2 divided by 3. Yeah. Yep.
Would it be wrong to have delta negative instead of -2?
You could show a delta negative, definitely. Yeah, I was just trying to emphasize the fact that it's not a -1/2, it's -2/3. Yep. All right.
Can you scoot over just for a second?
Scoot over. All right.
Do they all have to be the same atom to share a charge?
No, they do not. And we're going to cover that more. Oftentimes what happens is we'll show maybe 3 or 4 resonance structures, but some of them are equal contributors, and some of them are actually more significant than others. And that's when we get into major and minor contributors. And we haven't gotten there yet, but we will.
Can you back to the first ones? I mean the first example. But
All right, so now let's take a look at kind of some more tricky problems. And I'll just lead you guys through this example. So this next part, we're going to try to focus on identifying electrons that can delocalize. So I've got a CH3 here, bonded to a nitrogen, bonded to another CH3. Got a lone pair here. Got a carbon, double bonded to a carbon, and then a CH3. Let's try to draw the resonance structures for this. So I'm going to try pushing that lone pair into that position. Is that okay? No, if we do that, this top carbon right there would be above an octet. So we can't push an electron up to either of those CH3 groups. So that doesn't work. What about if I move these electrons down here? Is that okay? Exactly. We have to do 2 electron pushing arrows in this case in order to prevent violating the octet rule. If I only drew 1 arrow, we'd be breaking the octet rule. But what I can do is push these electrons onto that carbon, right? And that every atom has an octet, every atom's happy. So let's go ahead and draw this. So now we've got a CH3, got a nitrogen, got a CH3, carbon, carbon, CH3. And now this carbon has a negative charge on it. So we can go ahead and bracket this in, but I don't see any other potential resonance structures we can draw.
So you can do the left red arrow, so like the electrons going to Yeah, because it's going through two, right?
Yeah, so you always want to make sure that because we're starting with the lone pair and dumping it down, if we didn't draw that second red arrow, this carbon would have 5 bonds.
Okay.
So we need to break one of those pi bonds to make sure we don't violate the octet rule. Yep.
Why would nitrogen give up its electrons since it's more electronegative? Wouldn't it want to just keep holding?
So in this case, anytime we can show delocalization, we always try to show it using resonance structures because there is some delocalization. But let's go back to your point. Whoops, I forgot my positive charge over here. Which structure do you think is the predominant form of the resonance structure?
First one.
First one, why?
Nitrogen is more electronegative.
Because there's no charges.
Yeah, in this case, there are no charges on this one. That one is charged. So if we're thinking about major and minor contributors, the one on the left is going to be our major contributor because it doesn't have charge on that. And we're going to talk more about that tomorrow, too, when we do more practice. So let's go through and identify hybridization here. What's the hybridization for this nitrogen?
Oh, we don't know. No, it's gotta be in the P orbital.
It has to be in the p orbital in order to delocalize. So in this case, it must be sp2. All right, let's take a look at another example. It looks really similar to this one. We've got a nitrogen here, CH3. I'm going to slide this down. Is there a resonance structure for this molecule?
No.
Okay, let's, for the sake of the argument, try to move some electrons here. Wait for it. Frowning face, right? The reason that the electrons on this nitrogen can't delocalize is that there is no way of alleviating that Texas carbon. We would have to break a sigma bond, and we can't break sigma bonds in resonance structures. Yep.
So in order to move a lone pair, there needs to be some sort of double triple bond?
Yeah, exactly. If we're going to move a lone pair, there better be a p orbital on that adjacent atom. If there's not a p orbital, because this one's sp3, you can't push electrons there. So in this case, this doesn't work. And then, what's the hybridization for this nitrogen atom? sp3, because the lone pair cannot delocalize. And this is something that troubles a lot of organic chemistry students. Is you look at these two molecules, they look exactly the same. The only difference is a double bond. But the overall geometry and hybridization of the molecule changes radically due to the presence of that double bond. So we always have to watch out for that. So what I thought we would do is pull out our problem of the day from yesterday, problem of the day 5. And we'll take some time to work through this. So problem of the day number 5 is asking us to move electrons around. And so what I want you to do is to work with a partner or somebody next to you and try pushing electrons around, but make sure that you're not violating the octet rule with any of these. So So I'll give you guys a few minutes to work on this, and then we'll come together as a class and go through compound A or compound B.
Yes.
All right, so in this structure with compound A, what we can start doing is we can take the lone pair from that nitrogen, dump it down into the bond between the nitrogen and carbon, form a double bond. But if we don't do anything after that step, we violate the octet rule. So we must break one of those pi bonds, and then we dump electrons up onto that carbon. So now if we look at it, this carbon has a negative charge on it. This nitrogen has a positive charge. Can we keep on going?
Yes.
Yes. So let's try pushing these electrons all the way around. So let's say I move these electrons down here. Can I go like this?
Yes.
Well, then it has to go.
Then you have
Oh, I heard some people saying no. Why can't we do the second arrow? It breaks the sigma bond. We cannot break sigma bond. So in that case, we can't have that as a resonance structure. But what we can do is break this pi bond. Oops. And dump it onto that carbon atom. Does that make sense? So this negative charge is kind of getting delocalized all the way around the ring. Yep.
Is that why a lot of times with benzene rings, they draw the hexagon and just a circle in the middle to symbolize the resonance structure?
Exactly. Yeah, oftentimes with benzene rings, you see that dashed circle or even a full circle on the inside, indicating that a benzene ring doesn't have true double or single bonds. Those electrons actually delocalize, and the bonds are actually more like a bond and a half. Yep.
Can't we achieve that the circle inside the benzene ring without moving electrons from hydrogen?
We could. Yeah, definitely. So that is one option, but because we have a nitrogen with a lone pair next to it, that's also another option. So there are quite a few different resonance structures for this.
Where's that double bond going on the second one?
So if we look at the second one, this pi bond is actually moving its electrons onto this carbon. So now this carbon will have the lone pair with a negative charge.
Okay.
Yeah.
And then the H is gone.
The H is still on there. It doesn't violate the octet rule, right? Because it has one lone pair and then 3 bonded atoms on there.
Oh, okay.
Yeah. Yep.
So is that arrow on the second one, or is that pointing to the low pair?
Right here.
Yeah.
Yeah, so this lone pair on this top carbon is getting dumped down into this bond. So now this becomes a pi bond, and then this one gets broken from a pi bond into a regular sigma bond. All right, how about this? Let's work on this for the last remaining minute, and then when you guys come in tomorrow, hand in your best guess, or at least most gallant effort. I'll give you guys points for it. Remember to do the normal problem of the day too. And then I'll post the key online for this. But don't stress out if you don't get it perfectly on your first go around. Try to work in a group.